I've now provided a high-level introduction to what calculus is, the study of rates of change. We've distinguished the two main branches, differential calculus from integral calculus. I'd like to take a quick moment here now to show you a brief history of calculus. I think it's absolutely fascinating how long we've been tackling these problems, and so I want to provide you with that context, and then we'll use that context to jump directly into some hands-on examples of how calculus works. All right, we'll get to an explanation of who these guys are in a moment. They are the modern pioneers of calculus, but we're going to start off a long time ago, in 1800 years before the Common Era. So we're talking about 4,000 years ago. We have Egyptian papyruses that we found from that era that have area calculations on them. So that's similar to the kinds of integral calculus ideas that we were just talking about. And it was also quite a long time ago that something called the method of exhaustion, which we are going to cover on the next couple slides, was developed by Greeks. So Eudoxus in about 400 before the Common Era, so over 2,000 years ago, as well as Archimedes, also over 2,000 years ago, around 250 before the Common Era. And independently, the method of exhaustion was discovered by the Chinese Liu Hui, also around that same time as Archimedes did, the Greek. Jumping ahead a millennium to the 11th century of the Common Era that we're in now, the Arab Al-Haytham used integrals to calculate volumes. And Indians around the 14th century also had differentiation-like methods. So we had integral calculus and differential calculus, both being developed many centuries ago. But it wasn't until the 17th century in Europe with Gottfried Leibniz in Germany and Isaac Newton from England, who around the same time they were publishing papers, and there's quite a bit of contestation around who exactly was first, but independently, these two gentlemen in the 17th century developed modern calculus, the same calculus that we are using today, the same notation and early ideas that developed into all of the modern calculus principles that we have now. This includes the concepts of higher order differentiation and integration. So this is like how we took the first derivative and the second derivative of distance over time. So all those kinds of ideas have been around for quite a while. And this also includes rules like the product rule and the chain rule, which we'll get to shortly. Leibniz was the one who named calculus, and he also devised the notation that we will be using in these live lessons. Newton, on the other hand, was the first to apply calculus to physics, for example, to discover the laws of motion as well as gravity, which Newton is quite famous for doing. I mentioned at the top of this slide that we'd talk about the method of exhaustion, so let's do that now. To understand what the method of exhaustion is, let's start by talking about polygons. So polygons are shapes with multiple straight sides. So at least 3, which would be a triangle, or 4, which would be a rectangle, or another 4-sided shape. But typically we're talking about having 5 or more. So here's a 6-sided polygon, a hexagon specifically, and the Greeks figured out how to find the area of polygons like this hexagon by filling it with triangles. So we can calculate the area of this particular hexagon by breaking it into this rectangle in the middle and taking its height and width, multiplying that height by width, it gives us the area of this rectangle in here. And then we can use triangles at the top and the bottom of the polygon to calculate the area of this part and the bottom part. More specifically, the area of this chunk up here is half of the height g here times the width w. So g times w times half gives us the area of this chunk up here. And then we can do that same thing at the bottom here. G times w times half gives us the area of this chunk down here. We add those three chunks together, half times g times width, half times g times width, plus height times width. That gives us the area of the entire polygon, of this whole hexagon. The method of exhaustion builds on those ideas to find the area of curved shapes as opposed to straight-edged shapes. So let's say we have this circle and we'd like to figure out how much area this circle occupies. Well, you could use a four-sided polygon, a square, in here and calculate the area, and that's going to be maybe an okay approximation of the area of the circle, but you're missing these chunks here. So how about if we used a hexagon? Well, now we're getting a better approximation of the circle's area, but we're still missing 6 chunks off on the side. And then going to an octagon, an 8-sided polygon inside, well, now we're getting even closer. The area that we're missing is less and less and less. And so following this same idea through to exhaustion, so going to an infinite-sided polygon, that infinite-sided polygon approaches the shape of the entire circle, the area of the entire circle. So remember our two branches of calculus, differential calculus and integral calculus. Well, integral calculus is directly based on this method of exhaustion. And calculus in general relies on the idea of approaching infinity, as we're going to see shortly with a hands-on code demo. So this is why Leibniz gave this field, this study of the rates of change, why he gave it the name, this calculus of the infinitesimals, based on this idea of approaching infinity. Up next, we'll use code in Python and a couple of illustrations to cover this concept of calculus of the infinitesimals really precisely.